Good afternoon, everyone. My name is Chris Henry, and I'm a PhD student at the University of Missouri, Kansas City. I mainly work on computer vision problems like face recognition and video retrieval. Today, I'm here to present my work titled as Fast and Robust Video Deduplication. So nowadays, as you all know, there is an increasing usage of social media networks and mobile devices, and this have caused a surge in the video content being recorded and uploaded online. Consequently, this has also resulted in a rise in the illegal pirate videos. So these illegal pirate videos are basically the same, they contain the same content as the original videos, but with subtle variations. Let's say you can add some flipping to the video, you can add a filter to the video, you can add noise to the video, you can add your logo to the video. So people add these kinds of modifications to these pirate videos to dodge the video copy detection systems. So, and identifying these duplicates is known as video deduplication. So the main job of video deduplication is to find similar videos or exact duplicate videos. Also, managing a vast amount of video data is a significant challenge. And if we have the knowledge of these duplicate videos, it will help us in applications like video content management, and it is also helpful in copyright protection and video surveillance, etc. In this work, we are proposing a fast and robust video deduplication system, and given a query video, our system can retrieve the duplicate video in about 460 milliseconds with a recall of about 90%. And we tested this on a 1 million frame repository, which is equivalent to 145 hours of video. So this is the first part of our proposed method. Firstly, we need to represent the videos in the latent space, which as features. So we use different features to represent a video or video frames. So firstly, we take the video and we sample video frames from the video. And this feature generation is just for one video frame, the example shown. So first we have the input frame. We can extract, you see the blue lines, we can extract the shift features. Shift features are key points in the image, and then we can train a Gaussian mixture model. And using the trained Gaussian mixture model and the input image, we can run Fisher vector aggregation, which aggregates the feature to give a robust feature representation for the frame, and we get the Fisher vector of 1024 dimension. The second feature we are using is, you see the green line, the green boxes. This is simply a thumbnail feature. We just convert the frame into grayscale, and then we resize the frame into 12 by 12, and then we do some normalization, and we convert it into a 1D vector. So this is basically to represent the frame as a very abstract version. And then we do some dimension reduction on both the Fisher vector and the thumbnail feature to reduce the dimension. This is needed for the next steps of our process. And finally, we have after dimension reduction, we'll have a Fisher vector of dimension 128D and a thumbnail feature of 32D. The second step is using those features which we generated for the video frames. We need to retrieve those frames based on the features. So firstly, we need to build the 1 million frame repository. So we used a data set, FIVR 200K data set, which I will discuss about in the next slides. So we sample frames from each of the videos to generate a 1 million frame repository, and each frame in the 1 million repository will have a unique timestamp and a global timestamp and a unique frame ID. And then we generate the Fisher vector for all the 1 million frame. We generate the 1 million thumbnail features, and then for each of the features, we build KD tree for some fast retrieval of the features. So the top part is the building the KD tree. Now the bottom part is actually the frame retrieval, what we'll do during the test time. So let's say we have a query frame, and then we compute its Fisher vector, and we get the thumbnail feature out of that frame, and then we can search the KD tree with k nearest neighbor, and both the query trees will give us the indexes of the frame ID that it retrieved. And then we will use these retrieved indexes or the retrieved frame IDs to prune the video frames for the accurate video retrieval. This is the final part of the proposed method. This is called a temporal data pruning strategy. So as I told you in previous slides, each video is associated to a video ID. Each video has its own video ID, and it has a unique global timestamp. So in temporal data pruning, what we need to do is in the previous slide. So let's say from here, we have a single query frame, and then the returned indexes will be based on the number of the k during knn search. So if you choose k 128, you will have 128 plus 128 results. So as the number of k grows, so the number of frames that are retrieved also grow. So we need to prune the frames that are not correct. So firstly, in the first part, we do the video ID pruning. So as you know, each of the retrieved index has the video ID information. So we need to keep only video IDs which exist in all the sets. So if you see SQ of ID, it is a list of let's say 4 sets. So let's say we have a query video, and then we represent the query video as 4 frames uniformly sampled at a time step of tau. So we will have 4 sets, and then each of the set will have the retrieved frame indexes from for that particular frame. So 4 frames, we have 4 sets, and then each of this set will contain the retrieved frames from the query frame q tau of m. So we only keep the video IDs which will exist in all these sets. The second thing we do is, even after video pruning, we still have false positives in these sets. So we need to prune those as well. So for that, we use the global timestamp information. So as you know, the repository was built in a way that the frames were extracted at uniform time, at uniform steps. So we call those uniform steps as tau. We represent them as tau. And then what we can do is we can compare the timestamp differences between the retrieved frames in each set. And ideally, this timestamp difference should be equal to tau. So we keep all the frames whose when we take the difference of subsequent frames, the difference should be equal to tau. Once both these conditions are satisfied, then we can retrieve the final video. So a visual explanation is in the figure shown. So you can see four columns. Each column is represents the retrieved frames after pruning for the video frame, for each of the video frame. So you can see the green boxes. So you can see the timestamp TS 24.5, then TS 28.5, and then goes to 32.5, 36.5. So there is a coherency. It satisfies the video ID. The video ID is same. The timestamp difference is same. So we retrieve 2 videos, the one in the blue box and the one in the green boxes. The red boxes, those videos are not retrieved because in the remaining 2 sets we don't get that information. We cannot satisfy the criteria. So this is how the data pruning works. For the experimental data set, we are using the FIVR 200K data set. So this is a video retrieval data set. So it has different subsets. So particularly what we are interested in is the DSV subset. DSV subset is the duplicate scene video subset. So the videos in DSV share at least one scene regardless of whatever transformation is applied. Transformation like flipping, adding your logo, rotating the video, whatever. And overall, the data set contains about 225K video clips. However, only duplicate scene videos are about 7,500, and then these are basically YouTube videos. So the data set provides us with YouTube video links. So when we tried to download this, only about 5,100 videos were available for downloading. So we take these 5,100 videos, and one more thing, this data set has 100 queries. 100 queries means 100 different classes, so 100 different types of videos. And to build the repository, we extract 2 frames per second from these DSV labeled videos, and this makes us about, we can generate about a 1 million frame repository, which is equivalent to about 145 hours of video data. And for the testing, currently we take about 493 videos from the same repository, and we create augmented copies of the video. We add noise, we add blur, we change the saturation, we do flipping. These kinds of augmentations we do to dodge the system. And for the Curie videos, from these 493 Curie videos, we take Curie videos of duration 12 seconds. You can take any duration, it's up to you. Sorry, just we take 12 seconds Curie videos, and then we represent these Curie videos as 4 frames, so one at 0 seconds, and then so on. For the implementation details, this was implemented on Intel Core i7 12th Gen CPU with 64 gigs of RAM, and the entire system is built with Python. Just some part of the system, like the Fisher vector, the Sift key points, and the Gaussian mixture model training, is done on MATLAB because it has a convenient library for it. For the experimental results, we show 2 results. One is the recall, and one is the time consumption. For the recall, it means like in the retrieved video frames, in the retrieved video IDs, the video IDs we retrieved, the ground truth video ID should be in that set. If the ground truth video ID is not in that set, we don't get a correct result. We only get a correct result if the video ID is in that set. So we have recall at different values of k. K is the k value during KNN search, and as you can see, the accuracy will increase based on the increasing amount of, or the increase in the value of k. However, increasing the number of k will also increase the time consumption. So this is because the higher the k is, the more number of frames the KD tree will retrieve, and the more number of frames you need to process. So we need to find some optimal. There's a trade-off between the accuracy and the time consumption right now. So the table on the bottom, you can see the time consumption for different values of k and for different steps of the algorithm. So the top row, you can see the frame retrieval time per frame. So let's say we take the k equal to 512, so it takes about 98 milliseconds. The time is in milliseconds, so about 98 milliseconds. And then per Curie means, in our case, it's 4 frames because we represent the Curie as 4 frames. So per Curie, it takes about 393 milliseconds, and the temporal data pruning, the way we prune, it takes about 70 milliseconds. And in the last row, you can see the total time is about 464 milliseconds to extract the duplicate videos. And on the right, you can see the plot which shows on the x-axis, you can see the total time per Curie, and on the y-axis, you can see the recall. I'm not sure it's visible properly or not, but y-axis is recall. And the different dots are the results at different values of k. So it shows the same thing. As we increase the k, the time consumption and the recall will both increase. So in conclusion, we propose a fast and robust video deduplication system, and the system can retrieve from a large repository of about 1 million frames in around 460 milliseconds with a recall of about 90%. And we tested the system on the FIVR 200K dataset, and the results confirmed that our proposed system is invariant to typical rating effects. So in future work, we also we are trying to add some more small features to increase the accuracy and reduce the time consumption. And we will also test it on some more better test data. Thank you, everyone. Yeah.
Thank you, Chris.